Hi, in this video we're going to talk about some theorems about the Laplace transform, specifically this first one that's here in our notes, and then also about the table of Laplace transforms and how to use that. So I just wanted to zoom out so you could kind of see what we were going to talk about, and then I'm going to zoom back in so we can talk about each part. All right, so this is from our class notes. There are several theorems that are relevant to finding Laplace transforms and using them to solve differential equations. We're going to focus on this first one for right now, and then we'll come back and talk about some of these other ones a little bit later. All right, so remembering, like we talked about in the last video, that the definition of the Laplace transform of a function f of t is as an integral, an improper integral, for all values of s for which that integral converges. And so we looked at that a little bit in that last video. Generally, you're not going to actually have to evaluate that integral to find Laplace transforms. We have a table which you have in your notes packet, or you can find in lots of places. Our textbook has many differential equations. Textbook has a table of Laplace transforms. But in order to use that table of Laplace transforms, you need to understand a little bit about this idea called linearity of Laplace transforms. And the idea here is that a Laplace transform is an integral. And so when you have combinations of functions or constant multiples of functions, you need to think a little bit about how integrals work to understand how you might be able to find Laplace transforms of those. And so there's really two parts to this theorem. So the first part here tells us about how to find the Laplace transform of a sum of two functions. And remembering that the Laplace transform is an integral, and when you evaluate an integral, you can split that across the addition sign into separate integrals. You have to be a little careful with improper integrals. So provided each of the individual improper integrals converges, then you would say that that sum converges. But this basically just says if you have a sum of two functions that you want to find the Laplace transform of, that you can split that and find the Laplace transform of each function and then add your results together. Okay, so just like you do when you find derivatives and integrals. The second property here is also related to how you do integration. If you have a Laplace transform of a constant times a function, see, any constant, remembering again that the Laplace transform is an integral, and thinking about how you handle constants that are times a function you're trying to integrate, you have to pull that constant out front of that integral. And so this theorem says that you can also do that for Laplace transforms. And again, a little qualifier here at the end for all values of s for which all the Laplace transforms in this theorem exist. Okay, so there are some other theorems there, and we will come back and look at those in a later video. But I want to go to the next page of our notes here and talk a little bit about finding Laplace transforms of functions using the table. So here you see part of the table of Laplace transforms that is in your printed notes. There's also a PDF of it in Canvas. You can also pick up a printed copy in the Math Resource Center. There's many versions of this table in many different textbooks, but I'm going to be using this one and often referring to these line numbers. So it'll be helpful to you to use the one I've provided for our class. And so I want to talk a little bit about how this table is set up, and then we'll look at some examples of finding Laplace transforms of functions. All right, so in a prior video, we found a Laplace transform of just a generic constant function, and we found a Laplace transform of e to the t by using the definition. And all of these Laplace transforms can be found using that definition. The point is, though, that once somebody does that once, you don't have to do it for every single function in order to be able to use Laplace transforms. So I want you to pay attention on the table that we have here that there are two important things here in the header. So this first column is your f of t function, the function you're trying to find a Laplace transform of. And then to find the Laplace transform, you're going to look in that next column, and that notation at the top there tells you that that's what's in this column. So the Laplace transform of f of t, whatever that f of t is in the first column, gives you this f of s, which is your Laplace transform of that. So, for example, this first line of the table is telling us that the Laplace transform of 1 is 1 over s. And so you can kind of skim down here. I've got the first 7 lines just straight from our table, and then I skipped a couple, and then I have line 10 and 11 from our table here. And so most of this looks probably pretty familiar. You've got a factorial there, so sometimes you have factorials involved, right? But you know how to handle that. Line 4 probably should look a little bit unfamiliar. We will talk about that in the next video, what that thing that looks like a capital L is upside down is. It's called the gamma function. We'll look at that in the next video. Lines 10 and 11 of the table are the hyperbolic, sine, and cosine function, or sinh and cosh functions. So if you haven't seen those before, you might look those up. They come up in some of our homework, but they are hyperbolic sine and cosine functions. Got t to the n times e to the at. So most of the rest of this should look pretty familiar here. One thing I do want to say too, though, is that we have a complete table of Laplace transforms. You probably can't see this very well on the video screen, but I've kind of zoomed so I can fit the whole thing in the window. So complete table of Laplace transforms. This is the one that I've provided for our class. Again, you can look up many different versions of this. Our textbook has little bits of this in kind of different parts. But this is the one I'm going to be using in class, and this is the one I'll be referring to in notes. And so I might talk about line 14 or line 22 or whatever from the table. So it'll be helpful to you to use this version. And what I have on that other page of our actual notes are just a few select lines from this that we're going to use in these examples we're going to look at now. Okay, so let's look at those examples. So we are going to use the table of Laplace transforms to find each of these Laplace transforms. So I need to find the Laplace transform of 4t cubed plus cosh, hyperbolic cosine, of 2t. And that linearity theorem says that I can split that up and find the Laplace transform of each term. And then, in fact, even on that first term, I can pull that 4 out front. All right, and so then that's when I go and look at the table. You'll notice there's 2 lines on the table, lines 3 and 4 on our table, that are the Laplace transform of t to a power. So t to the n, where n is a positive integer, and t to the p, where p, the only restriction on p for that one is that p is greater than -1. So technically I could use either of those, although we haven't talked about what the gamma function on line 4 means yet. And since I'm taking the Laplace transform of t cubed, 3 is a positive integer, so for that one I'm going to use line 3. And our n here is 3. And then for the second term, for the Laplace transform of the cosh function, be careful about that. Line 7 is the cosine function, and line 11 on the table is the cosh function. This one's the cosh function, so make sure you're looking at the correct one. So I'm going to be using line 11, and our A is 2. Okay, so now I'm just going to do what it says for the right-hand side of the table for each of those. So I'm going to have this 4 out front for my Laplace transform of 4t cubed. So 4 is out front. Laplace transform of t cubed tells us we're going to have 3 factorial over s to the 3 plus 1. And then for line 11 on our table here, for the Laplace transform of cosh of 2t, we're going to have s over s squared minus 2 squared. Remember that our a is 2. All right, so I could leave them in that form, or we can go ahead and simplify them. And remembering that you're really going to be using this to solve differential equations, maybe you want to go ahead and simplify them. Again, remember our goal is really to solve the differential equation. I haven't done that yet. We'll do that soon. We're just kind of doing little bits and parts of the problem. All right, so for these others, One important thing to notice is there's actually only one of these others that is really explicitly in our table. For number 4, I do have sine of 3t and I have cosine of 3t, but you know that when you integrate functions, you can't just integrate a product of functions by integrating each part. So remembering that the Laplace transform is an integral should help you understand that you can't just find the Laplace transform of each part. You're going to have to do something a little bit more creative for number 4 to find that Laplace transform. Same thing with number 5, so I'm going to have to do something with that. Number 6, there are Laplace transforms for powers, but they're just powers of t. So I can't do it with it exactly as it's written. Number 7 actually is in the table, and that's line 16. So let's go ahead and do that one, because that one's kind of the easy one here. So Laplace transform of t times e to the 2t. I'm going to be using line 16. N is going to be 1 and A is 2. You'll probably find it helpful to write these little notes to yourself so that when you put those numbers into your Laplace transform, you're putting the right number in the right place. Okay, so just using what's on the right column for that table there, I have 1 factorial over s minus 2 to the 1 plus 1. Or I could rewrite that as 1 over s minus 2, the quantity squared. Okay, for these other 3 that are in the middle here, I'm going to have to rewrite those so that they actually match what is in the table. For 4 and 5, I'm going to have to use a trig identity. And for number 6, I'm just going to use some algebra and expand that out. This might be a good time to pause the video and try it, and then restart the video to check your work and see if you did it correctly. All right, so do some homework over these. In the next video, we will look at what that gamma function means and do some problems involving that and a couple of other theorems, and then we will solve some differential equations.